This video will cover Section 3 of Chapter 7, where we'll continue our discussion of sampling error. We'll talk about the distribution of the sample proportions relative to a population proportion. We'll talk about the mean and standard deviation of that distribution and use that sampling distribution to calculate probabilities. We'll also talk about the central limit theorem again and talk about where it's appropriate to use that with regard to a sample proportion. So population proportion, that's going to be a population parameter measure. It measures the entire population. It's the fraction of the values in the population that take on a specific attribute. We denote the population proportion with the Greek symbol pi. The sample proportion is the fraction of the items in the sample that have the attribute that we're interested in studying. Little p is our sample proportion. Our sample statistic, p, is our best estimate for the population parameter pi. If there are only two outcomes, our population proportion pi is binomially distributed. In cases where we can treat it like there's only two outcomes, this population proportion still behaves binomially. So let's talk about sampling error for a proportion. The sampling error is basically calculated the same way as we would do with a sample mean. We take the sample proportion and we subtract out the population proportion. The difference between those two values would be how far off our sample is from the population value. If this number is a positive, then our sample is relatively high compared to the population. If this number is negative, that means our sample portion is small relative to the population proportion. So to actually calculate sampling error, we would have to know the population proportion. Suppose we had a population that contained 100 people. 80 of those people had the attribute of interest. So our population proportion is 0.8. We would need to compute the sample proportion. Suppose that we just collected a random sample of 12 individuals. Of those 12 individuals, 9 of them had the attribute of interest. That's a proportion for this sample of 0.75. To compute the sampling error, we take that 0.75 and subtract out the population proportion of 0.8. The sampling error here is minus 0.05. The sampling distribution of these sample proportions is approximately normally distributed if the sample size times our population proportion is greater than 5, and the sample size times 1 minus our population proportion is greater than or equal to 5. If those two things hold, then we know that our sampling distribution is approximately normally distributed. So we would have a distribution that looks like the yellow bars, and we would say it is approximately normally distributed, like the red curve that's drawn above that. If that's the case, then the mean of all of those sample proportions is the population proportion. The standard deviation of all of those sample proportions is the square root of the population proportion times 1 minus the population proportion divided by n. This is Theorem 5 in your textbook. We can calculate a z-value for proportions. The z-value is written like this. That sampling error goes on the top, so our sample proportion minus our population proportion, how far apart are the sample and population values, divided by the standard deviation. So divided by the square root of that pi times 1 minus pi divided by n. If we have sampled without replacement, and we have picked a relatively large sample size, where the sample size is greater than 5% of the population size, then we must use that finite population correction factor that we talked about in the last section. So we'd have our standard deviation, and we'd multiply that by the square root of the population size minus the sample size, divided by the population size minus 1. To use the sampling distribution for the proportion, we've developed an example here. Suppose you take a random sample from a population. That sample contains 100 items. Of those items, 73 of them contain the characteristic that we're interested in looking at. To be able to say anything about this, we need to know the population proportion. So pretend that we know that, and that population proportion is 0.8. Calculate the sample proportion. Our sample proportion is x, or 73, divided by n, which is 100, or 0.73. So we know 80% of the population contains this attribute. 73% of our sample contain this attribute. Derive the mean and standard deviation of the sampling distribution. So what's the center of this distribution of all the possible sample proportions we could get? Well, the center of that distribution is also the center of the population distribution. The population is centered at 0.8. The standard deviation of all of those sample proportions is the population proportion times 1 minus the population proportion divided by our sample size of 100. That turns out to be 0.04. The next thing to do is to define the event of interest. So suppose we're interested in knowing the probability of getting a sample proportion less than or equal to 0.73. Now, how would we do that? So start by being sure that we can apply the normal distribution. If n times pi and n times 1 minus pi are both greater than 5, we can use the normal distribution. So let's check that first. N times, this is supposed to be pi, n times pi, or 100 times 0.8 is 80. That's definitely greater than 5. And n times 1 minus, that's again supposed to be pi, sorry for the error. N times 1 minus pi, n is 100, 1 minus pi would be 0.2, 100 times 0.2 is 20, so that's also greater than 5. Since both of those values are greater than 5, we can apply the normal distribution. So the next thing to do would be to draw a picture. So we'll draw a picture here. Draw your x-axis, or in this case, it's our p-axis, sample proportion. Draw the bell curve over top of that. It does not have to be perfect, right? We just want something that looks like a bell curve approximately so that we can get an idea of what we're trying to do here. The center of this distribution is 0.8 because that's our population proportion. The standard deviation of this distribution, or the standard deviation of all of those sample proportions, we calculated on the last slide to be 0.04. We're trying to find the probability of getting a sample proportion less than or equal to the 0.73 that we got with this particular sample. So we can use norm dist to calculate this since our normal distribution applies. We would go equals norm dist of 0.73 because that's the thing we want to find the probability of. Our mean would be 0.8 because that's our population proportion. Our standard deviation would be 0.04 because that's our standard deviation of all of those sample proportions. We put in true to get it to add all the probabilities together for us. If we plug this into Excel, we get a probability of 0.0401, or there's about a 4% chance that we could get a sample proportion of less than or equal to 0.73. You could also do this using the standard normal distribution table. So you would have to take your 0.73 and convert it into a z-score. So here I've taken 0.73 minus 0.8, divide that by 0.04, and I get minus 1.75. In other words, this 0.73 is 1.75 standard errors below our 0.8. The probability will be the same looking in the table as it is when we use norm dist. We're still going to get this 4% chance of being less than or equal to 0.73. Here's another example. If the true proportion of voters who support Proposition A is 0.4, or 40%, what is the probability that a sample of size 200 yields a sample proportion between 0.4 and 0.45, or that sample of 200 would have 40 to 45% of the voters supporting Proposition A. So given our population proportion of 0.4 and our sample size of 200, what's the probability of being between 0.4 and 0.45? The first thing we need to do is calculate the standard deviation of that sampling distribution, or the standard error. We take the square root of 0.4, sorry, that 0 fell down, not sure what happened there, of 0.4 times 1 minus 0.4, divide by 200, and then take the square root of that. If we do that, we get 0.0346. Now we can convert these 0.4s and 0.45s into z-scores. We'll find out the probability of being between 0.4 and 0.45 is the same as the probability of being between 0 and 1.44 standard errors above the mean. We can use Excel to do this, or we can use the standard normal distribution. Either way, we're going to find the probability of being between 40 and 45% of the voters in that sample of 200 supporting Proposition A to be about 42.51%, or 0.4251.